Good morning and welcome to today's Military and Aerospace Electronics webinar. How are platform power requirements driving designs for modular systems for air and ground vehicles? This event is sponsored by Elma Electronic. I am Jamie Whitney, Senior Editor of Military and Aerospace Electronics with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please note them in the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Military and Aerospace Electronics website within the next 24 hours. You'll be notified by email when the archive is available. Now, I would like to introduce our speakers for today's discussion. As Director of Engineering for Bellman Electronics, David Gash has 12+ years of experience in power supply solutions for various industries, including embedded systems and motor control. He is an active participant in open systems standards, including VITA and SOSA. David holds a bachelor's and master's degrees in electrical engineering from Stony Brook University. Ken Grobe is Director of Embedded Technologies for Elma Electronic. He is responsible for driving the company's integrated platform solutions. He is a highly respected technical expert in embedded computing, open system architectures, and a leading contributor to VITA standards and the SOSA technical standard. Ken holds a BSEE from Drexel University in Philadelphia. Welcome, David and Ken. Please go ahead.
Thank you, Jamie. Hello, everybody. My name is David Gash, and as Jamie said, I am Director of Engineering for a company called Bellman Electronics. And today we're going to be talking to you about how the platform power requirements of the various military platforms are driving the design for modular systems, and particularly focusing on both the air and ground vehicles. So to start, each platform has its own unique form of power generation, whether it's a fighter jet, aircraft carrier, helicopter, or tank or ground vehicle. And all of these have different parameters for which a system that is designed to operate or be installed on that platform needs to be able to work with. And that includes things like the capabilities of the power generation, thermal and mechanical requirements. And they all have different varying levels of the quality of their source. Obviously, the bigger the platform, the more room can be dedicated towards generating the power, and so that generally means cleaner power, whereas the smaller platforms tend to have worse power generation and thus need to have more requirements. So we're going to, as I said, we're going to be focusing on both the vehicle power, which is defined by MIL Standard 1275, and the aircraft power, which is defined by MIL Standard 704. And we're going to be talking about them in generalities, as well as some specific challenges that these standards pose that make developing systems for these platforms a challenge. So as I previously said, vehicle platforms is not always a constant power. Just like if you have your power from your wall, you like to say that it's constant, but it varies a lot depending upon what else is going on on the system. For example, you can have a large load that is turning on and off, which is creating either sags or spikes to your line. You can have platform-specific performance parameters, such as perhaps needing to operate while turning over a combustion engine or transferring from one power source to another power source. And these are different for every different platform because the way that the platforms generate electricity is different. For example, on a ground vehicle, you typically have a battery and an alternator that is used to generate power, whereas on an aircraft, you're likely to have some sort of auxiliary power unit or a generator built off of the engines. So for a lot of military systems, people want, what they call 28 volts in. And that 28 volts, even under normal conditions, is not always 28 volts, or very, very unlikely to be. So this is kind of a snapshot of general requirements for both Mil-Standard 704, which is the standard that specifies basically the power that's on military aircrafts, and Mil-Standard 1275, which is similar for vehicle power. So you can see here that top line, steady state voltage. That basically means that that the bus can be indefinitely between those two ranges. So you can see on an aircraft, it can be between 22 and 29, and on a vehicle, it can be between 20 and 33. So you can see right off the bat, the power on an airplane is different than the power on a ground vehicle, even just in where it normally lies. Beyond that, there's other finer details that are different. For example, the ripple is different based off of what platform it is, and as well as the transient voltage. So how wide can the voltage go temporarily? On an aircraft, the latest versions of the standard have it go up to 50 volts, and on the vehicle, they can go as high as 100. And all equipment needs to not necessarily operate, but not be damaged by any of these transients. So looking at this, you can see that a vehicle power system has to be more operationally resilient than potentially one for an aircraft. So on this slide, you can see here the envelope for Mil-Standard 1275, and on the right-hand side, you can see kind of the nominal range of 20 to 33, and then as you go, you can see the extremes of the transient performance, with the x-axis being the time. This is basically the description of where the white is where you expect to be operating, and where the gray is on the bottom, it indicates that you may lose performance, and on the gray on the top means you may damage the power, the product. Mil-Standard 1275 also has other various requirements. One of them, which is probably the most has the most effect on system design, is what they call the initial engagement surge and cranking surge. So when you turn over your vehicle, the starter, which is an electric motor, has to pull lots of current to be able to turn over the internal combustion engine, and as such, the voltage of that battery sags quite a lot. You could probably have noticed this in your vehicle at home if you try to turn over the engine and you can see the lights dim on the dashboard, or your radio turns off. It's the same concept here. And critical equipment on the vehicle must remain operational. And this poses a big challenge because that voltage can go as low as 12 volts. And looking at this curve, you can see here that 12 volts can be present for a second. That, as far as electronics are concerned, 1 second is a very long time. It basically means you have to be able to operate at for all intents and purposes, a steady state at that level. This poses a very large challenge from the power systems perspective, as the current required to basically go down to 12 volts, the current that you need to pull increases, because for a power is equal to voltage times current. So for equivalent power level, the lower the voltage, the more current you have. This puts a lot more stress on the components and the power supply in general, and thus it makes a challenge, usually requiring derating of the product for operation. Mil-Standard 704 is a little bit more of a less targeted standard, because aircrafts have many different power buses. they could have 28 volts, 270 volts, three-phase AC, single-phase AC, and there's upwards of 8 different power forms that are available on an aircraft. For the purposes of this conversation, we're just going to talk about the 28 volts. And similar to the 1275 curve that we saw, we see the same kind of curve for the 704 28 volt bus with the peak of 50 volts and the trough of 18 here. Again, if it operates above this line, it isn't expected to be, you can't expect the product to necessarily survive. Below this line, you can't expect it to be operating. And then in between, you would expect it to be its normal operating envelope. Mill standard 704 does have a special consideration that is unique to itself, which is what is typically called hold up, but it's actually officially called power transfer in the standard. And essentially what that is when you're on the ground on an airplane, the ground station is going to be providing you power for your electronic equipment. You'll have an umbilical that goes to whatever equipment you have on the side, and that will be used to power while you're on the ground. When you are preparing to taxi and take off, you will transfer powers from that ground station onto the onboard APU, at which point that transfer takes a period of time. And it's usually characterized as being 50 milliseconds. And that's where the colloquial name for this as being 50 millisecond holdup comes from. This this basically poses a challenge from a swap perspective, because the energy that is required to basically operate your system during this transfer has to be contained on board. And in most cases, this is in the form of capacitors. And they're just a physical constraint that you have to have so much capacitance and so much energy storage devices on this on this platform to be able to provide the holdup that you need, that it basically drives mostly the size and the weight of the product, as you have to have extra elements that may not necessarily be needed if you didn't have to meet this requirement. Here you can see what Bellman would call a holdup card, which is kind of a power conditioner, which accepts 704 power at the input and provides 704 power at the output, but it provides holdup for that power. So you can see this teal line, and you can see here that while the dark blue is going to 0, the teal does not reach 0, thus allowing the back-end system to continue to operate. So how are these challenges being solved by MOSA? So the VITA committee, VITA 62.0, is a standard that defines a bunch of power modules or power supply cards. These provide many different options for the user to be able to select, and includes power supplies that have various different input power forms, as well as power conditioners and energy storage modules that can help meet these requirements. And whether that's a holdup card, as we discussed previously, or a transient suppression device that might provide some protection over those 100 volt or 50 volt transients, or other types of modules in there. And this ecosystem has developed with multiple vendors providing solutions. And in a lot of cases, these different solutions can be drop-in replacements for each other because of the way that ANSI VITA 62.0 is written. This standard has also been leveraged by the SOSA technical standard and is used leveraged by that and defined further inside of the SOSA technical standard. So as an example here, we have 2 different products, what we call the VPX 800D IQI and the VPX 500M, DW IQI. These are products that are drop-in replacements for each other, but are targeted towards different platforms. So if you have a system for which you need to put it on an airplane, you can plug in the VPX 800D IQI, and it will provide all the needs that you need for that. But if you want to take that system and put it on a vehicle, all you would need to do is unplug the 500 DW and plug in the unplug the Android D and plug in the 500 DW, and you would get a power supply that meets the middle standard 1275 along with the cranking and initial engagement surge specifications. The one thing you will notice that, as we discussed, because of the need for going down so low, you do trade output power capacity for being able to do that. The vehicle version is lower power because of that. With that said, I'm going to turn it over to Ken, who's going to discuss how to take these MOSA solutions and integrate them into the system.
Thanks, Dave. So David's, in his introductions, gone over the different requirements that we have for the power supplies in vehicle applications versus aircraft applications. So I'm going to speak to now how what the system some of the system considerations are when we're looking at applying power supplies that meet those specifications at the next higher level. So as Dave mentioned, the power supplies are typically designed to V262, and this defines or provides the definition for the power supply, including its size and how its interface is defined between it and the rest of the system. So the picture to the right is a chassis, and when we consider building a system, we need some place to hold the cards that implement it and a package that's appropriate for mounting in the platform. Then we also need to consider how we mate the power supply and how we connect it into the system. So the green section on the right side, top right, is called a backplane, and this is how we interface the cards together in the system, plugging them into slots. In this case, it's defined through the OpenVPX standards. The connector on the far right, the black one, is actually how we interface the power supply. What's convenient about this is that the power supplies are defined in a 3U plug-in, and we have a mating connector that plugs into the backplane. So the power supply is basically modular, it's removable, and it's pluggable. The chassis that we're showing is conduction cooled, meaning that the cards are designed for conduction cooling. So we have a channel or slot that the power supply plugs into, and heat's transferred away from the power supply through the rails and then to the outside world. So the good thing about this is the power supply is modular, and to connect it is all that one needs to do is simply plug it into the slot. So other considerations, as David pointed out, would be hold up and how that's implemented. The hold up solution's usually implemented in a separate module, so we need to find a space for it in the chassis. And in this case, we're showing the hold up module mounted on a plate that's in the front. The hold up modules that provide additional energy storage for the system during events can be mounted fixed, or they can be removable. So you can plug them into a slot, and they can be removable just like the power supply, or they can be fixed mount. They're available both ways. So a benefit of following the V262 standard and defining the power supplies in a pluggable module format is that one solution or one physical implementation can be used to multiple platforms, this being aircraft or ground. So as Dave discussed, we've got some trade-offs to consider in the power supply design. When we're considering the standards, vehicle standard 1275 versus aircraft standards, we've got issues like engagement or starting, which pulls a lot of current at a lower voltage, causing it to sag. What this causes us to do is look at how a power supply is designed internally, because we've got the needs to operate at a lower input voltage for a period of time, driving more current. So what has to happen is that the power supply itself is beefed up. It's got to be able to have heavier components because of the currents that it's handling in those conditions. So this is not typical of all supplies, but typical potentially of a vehicle application. So here we're looking at a wider range of inputs. What this does is it puts pressure on the total amount of power that we can deliver from that power supply. So it's reduced. What this is doing, the designer of the system is making them consider how do they get enough power from a power supply into the system, and consider that for a wider range supply, potentially they'll have less of an output than they may have, say, for the mill standard 704 supplies Dave showed before. When we're looking at the wide range supplies, we might get about 500 watts out of the supply. And when we're looking at the power supplies for mill standard at 704, we get around 700 or 800 watts. Another consideration in the system implementation is something called chassis management. Chassis management, when we're looking at SOSA and CMOS systems, is a requirement. This is a two-wire interface that connects the PICs, the boards that are in the system, to the other boards that are in the system, along with now an intelligent power supply that must also be able to communicate on this intelligent platform management bus. What this allows the system manager, or the chassis manager, to do is communicate with the power supply, get information from it to see that it's okay, also be able to send certain control signals in it and actually be able to turn it on and off or inhibit its operation. Use of the pluggable supplies aligned with VDA62 is something we've talked about, whereas VDA62 is actually the standard that defines how the power supply is implemented, its size and its characteristics, and the signals and the voltage rails that are implemented in that. One other thing that we might need to consider, or two, would be scaling. For instance, if one supply doesn't supply enough power for you, then you may actually have to include more than one, which is allowed and doable. And another point would be, if you're looking to improve your overall, let's say, availability and reliability, you have the option to do something called N+1, which is to replicate a power supply, not use more than one supplies as far as power, and then have another one that's sort of a standby unit that will take over in case one of the two power supplies fails. So these considerations are built into the designs of the power supplies to allow them to be able to be scaled, or allow them to be able to be used in N+1 configurations. So digging down a little bit deeper, what does VDA62 do for us, and what are some of the characteristics of the power supplies themselves when we build them into a power system? When we look at the SOSA and CMOS specifications, they're now specifying that power supplies should be 12-volt centric. What this means is that the rail scheme has changed now, and the newer go-forward strategy is to have a two-rail implementation, providing 12 volts as the primary and then 3.3 aux. Prior power supplies had multiple rails, +5, +3, ±12, etc. And that's called the legacy implementation. Both of those implementations still exist, but when one designs for a current system around a 12-volt centric supply, you have to realize that, in fact, that supply now provides two rails, where if you were going to mix these supplies, you have to think about that there's two different definitions for them today. So there's a legacy definition and a 12-volt definition. So typically we'd use all of one type in a system where the power supplies are 12-volt and 3.3. When we look at what VDA62 and the new definition has done, there's some other features that have been added. One is this MVMRO signal. It's been added as a requirement, which protects the information that's stored in memory devices and makes it write protected. And then we've also seen considerations for the intelligent platform management bus for smart power supplies to add intelligence to the supplies. So what's been removed is the plus and minus 12-volt rail and the or the plus 12 and minus 12 rails are removed for one common supply rail of 12 volts, where we used to have 5, 12, minus 12, and 3.3 and 3.3 aux. So another consideration of the power supply are share lines that are used for current sharing between the lines. And typically manufacturers, there's these lines that are defined, and manufacturers develop a strategy to make the power supply share current so that you can scale multiple power supplies in a power system. So what you end up with is a more, let's say, simplistic approach and a two-rail design, intelligence being added through VITA 46.11, and then the NVMRO signal added for write protect. And as I said before, one needs to be thinking that you need to be careful you don't mix the two types of supplies that might be out in the market. If you need multiple rails, they're still available. If you want 12-volt centric, that's a specific implementation under the VITA 62 specification. So looking and taking another look at how we mount these, look closer view here of the backplane mounted inside the chassis, and we can see the VITA 62 connector. And to the right, what we see is how that power supply looks when it's mounted into the conduction slot and plugged in and mated with the connector on the backplane. The beauty of that is it's simple, it's easy to replace, easy to insert. There's no extra wires that you have to worry about because this is a pluggable interface that's designed to carry the current. That's another consideration, the backplane, that we have high currents coming out of the pins on the VITA 62 connector, and we need to have appropriate power plane designs to transfer the power down through the backplane to each one of the slots that are in it, where each card in that backplane is taking power from the backplane provided by the power supply to power the card. So the beauty of following a standard like VITA 62 and the benefit would be that you can have one type of supply or let's say building blocks that are allowed, the power supply itself, the hold-up module, etc., and be able to use them in different types of chassis. So the chassis size and envelope may differ for the application. In this case, what we're showing on the left is a chassis that's designed for a vehicle application, designed to the SAVE specification, where it's got an isolation plate and it's mounted on that plate in a specific envelope. If we were looking at a chassis for an aircraft application, in this case on the right, it can use the same kinds of supplies that can be used in the vehicle application on the left. So you sort of have one approach for the way that the power supplies are packaged and the way that the interfaces are defined. And we can use them and then in different types of chassis, in this case an ATR for the aircraft application that mounts differently in a different space envelope because of what the platform requires. So it gives us a family of common building blocks that makes it easier to produce power systems that can align with various applications that are out there with one approach. So where we end up is a well-defined implementation, this two-rail design with 3.3 aux with intelligence and the ability to share current to be able to scale. And we implement VITA 46.11 or the chassis management interface for systems management so that we have some way to look at this power supplies for reporting and for control. So that brings us to the end. So just taking wrapping up here and looking at what we've talked about today. Power requirements vary, as we discussed, depending on the platform and the application. So for aircraft, the requirements are driven by MIL Standard 704, and for vehicles, MIL Standard 1275. As Dave showed in his charts and described that the input quality varies depending on the platform, and the range of the transients also vary. And then we have various things to consider, such as switchover interruption in aircrafts when you're transferring from ground power to aircraft power. And then in the vehicles, a different type of requirement that is driven by the starting engagement, where we have a heavy current demand on the vehicle battery system, pulling down the voltage, which makes us have to consider operating at much wider ranges on the input voltage to the supplies. So things we need to make sure we cover is that wide input voltage range in both applications, a little different for each one. And then whether a hold-up system is necessary in vehicles, it typically is, and how we implement that. In the case of the vehicle design, there's not enough room in the power supply to do it, to package the voltage. So we're doing it with something called a hold-up module, which is an additional component that's considered in the power supply implementation. So VITA62 provides the standard for the modular power supply designs and the form factor. And as discussed, this can be used in both aircraft applications and chassis designed for aircraft, as well as in vehicle applications. SOSA has sort of advanced the power scheme and moved those recommendations or requirements that are in SOSA to VITA, where they've been incorporated in VITA62, which gives us a newer 12-volt centric approach to the power supplies, and also options for intelligence included through 46.11. Then lastly, the VITA62 family of pluggable supplies and hold-up modules provide an off-the-shelf implementation that makes it a little easier for system builders to take products that are predefined by the ecosystem to apply to implement the power supply systems that are required for various applications. So with that, I'll turn it back to Jamie for Q&A. Thank you.
All right. Thank you so much, Ken and David. A few of you have already submitted questions, so we're going to jump right in. As a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. I would also like to note that material from today's presentation, including the slides used by Ken and David, are available for download, and today's presentation will be available on the Military and Aerospace Electronics website within the next 24 hours. Okay, and our first question, what if my system does not require operation during vehicle startup or power transfer? David?
So the one thing that's good about this whole modular approach is that if you don't need something, you just don't need to use it. So for example, if you're deploying a system on an aircraft, but you don't have a requirement that your system operates through the power transfer, you could just not use the hold-up module, and the power supply portion of that will handle everything else. So while you may not need to use the power transfer, but you operate during that power transfer and therefore not need all that energy storage, you will still need to operate through all those transients that were shown in the presentation. So you can't get away with a very simple power supply. You still need something that's somewhat ruggedized, but you don't need to pay the swap penalty for having all that energy stored up. On the opposite side, for the vehicle, for the startup, initial engagement surge, and cranking, again, if you don't need to operate when the voltage drops below 18 volts, you can then just use a power supply that does not have the low wide range input range, which then probably means that you can use a higher power product. And again, the beauty of this modular system is that you unplug one and you plug in another, and you're good to go.
Great, thank you. And Ken, a question for you. Can I combine power supply plugins to increase the overall system power available?
Yes. The design considers that they could be scaled, so you can plug in, say you need the power of 2 supplies. If you're in the wide range, you might need 1,000 watts, and you could do that by combining 2. You can actually use more than 2 if you need more than 2. So yes.
Thank you. And what about surface ship and submarine applications? David, do you have any thoughts on that?
So yeah, this presentation is mainly focused on Milstern 704 and Milstern 1275, which are the specs for aircraft and vehicle respectively. There is actually one for naval applications, which is Milstern 1399. That one is largely similar in its content, although the power forms on a ship don't necessarily align completely with the ones that like they do, for example, comparing the 28 volts between a vehicle and a plane. As such, equipment that goes on a naval ship is typically a little bit more, is not necessarily directly comparable. And also because typically the ships have more space, not only is the power better behaved, but the equipment itself can be physically larger to meet the same requirements.
Got it.
So Milstern 1399 would be the standard that you would look at, and it would contain a lot of the same information that we discussed here today.
Thank you. And Ken, can the power supplies be monitored by a chassis manager?
Yeah. So as the power supplies have evolved, not all power supplies prior had this capability. It wasn't really deemed necessary till more recently. But now for an intelligence, the power supply has to have like a small microprocessor in it to be able to respond to commands that have to do with monitoring that would be coming from a chassis manager that's mounted somewhere in the system. That chassis manager would be communicating with the PICs, the other cards in the system, as well as the power supply. It'd be looking for things like nominal voltage rail compliance, that the power supply is within tolerance. And it can also do things like communicate to the power supply and give it a command to maybe turn itself off or turn itself back on, for instance.
All right. Well, gentlemen, thank you so much for your time and your expertise. That concludes today's presentation. On behalf of Military and Aerospace Electronics, I would like to thank our speakers, Elma Electronic for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of the day.
Thank you.
Thank you. Have a good day.